Today we're going to talk about infinite limits. So infinite limits are when we have a limit when there's a vertical asymptote. So when there's a vertical asymptote, the limits from the left and the right of the asymptotes are going to be infinite limits. Because as we approach an asymptote, it's going to go towards infinity or towards negative infinity for every time we have vertical asymptotes. When you're able to graph, go ahead and graph and then use the graph to help determine the infinite limits. So if we look at this first example, what we're going to do is go ahead and figure out where those vertical asymptotes might be by factoring and simplifying. So for this one, we've got the numerator can be factored as x plus 4 times x minus 2, and the denominator can be factored as x plus 2, x minus 2, because it's a difference of squares. So we know just by looking at this equation, we have a whole at x equals positive 2 because that cancels out. And we should have a vertical asymptote at x equals negative 2. If we were to graph this, it would look something along the lines of this. So we've got our axes. And then we know that at negative 2, we've got a vertical asymptote. At 2, we've got a hole. So as we graph this, you will see a trend with our graph. So if we look at this graph, what can we say about where our left-handed limit at negative 2 is going to be? So what would you say is our limit as x approaches negative 2 from the left of f of x? So if we look at our graph, it looks like as x approaches negative 2 from the left, we are approaching negative infinity. And then if we look at the limit as x approaches negative 2 from the right of f of x, what does it look like our limit is going to be? Hopefully you got positive infinity. So it is possible for our limits to be infinite, but what does that mean for any manipulation? So we've got some different properties of infinite limits. And so we're going to just assume that c and l are real numbers and f and g are functions such that the limit as x approaches c of f of x is positive infinity, and the limit as x approaches c of g of x equals l. So basically, as we approach some value between these two functions, one of them approaches infinity, the other one just approaches a number. So if we do the sum or difference of these two functions, it's going to be positive infinity, because no matter what you add or subtract from positive infinity, it's still going to be positive infinity. Product, as long as that constant is positive, when we multiply these two limits, we will get a positive infinity. And if we have our constant as a negative value, because then it would be negative times positive, it is in fact negative infinity when we find this limit. Quotient rule, if we have a limit that approaches infinity on the denominator, our value is just going to be 0 for the limit. These properties also hold true for one-sided limits and for functions for which the limit of f of x as x approaches c is negative infinity. So these are just the examples using positive infinity and a constant with double-sided limits. So let's look at a couple examples really quick. The first one, we're going to be given that the limit of as x approaches 0 of 1 equals 1, and the limit as x approaches 0 of 1 over x squared equals infinity. And we're looking for the limit as x approaches 0 of 1 plus 1 over x squared. So which property do you think we're going to use for this one? this one, we will be using that sum or difference property, because you'll notice we have two separate functions where one is infinity, and down here we've got two separate functions where one of them's infinity. So when we add these, because it's positive infinity, the limit as x approaches 0 of 1 plus 1 over x squared is going to be positive infinity. So then if we look at the next example, we've got the limit as x approaches 1 from the left of x squared plus 2 equals 2, and the limit as x approaches 1 from the left of cotangent of pi times x equals negative infinity. We are looking for the limit as x approaches 1 from the left of x squared plus 1 over cotangent of pi x. Which property do you think we will be using for this one? If we use quotient property, notice that in the denominator, that is where we've got our infinite amount, but it's negative this time. So in the quotient property, it's positive in our example, but this one is negative. Does that actually affect the value? No. So instead, it actually just ends up being 0 again because of that quotient property where infinity is on the denominator, and if we get infinitely larger on the denominator, that just means our fraction is getting infinitely smaller and close to 0. So for this one, the limit as x approaches 1 from the left of x squared plus 1 over cotangent of pi over x equals 0. We've got one more example for this one. I want you to go ahead and try it on your own. Which property did you use for this? So you should have used product property because we're taking the product of a constant and infinity, because the constant is positive and infinity is positive. We know that the limit as x approaches 0 from the right of 3 cotangent of x is going to be positive infinity.